I will begin with a word of prayer, possibly for the first time. Dear Heavenly Father, we thank you for this day, and we thank you for these students. Just help us again, Lord, to glorify you what we do. In your prayer, Lord Jesus. Amen. All right. All right, so basically here I'm back in Haberman, page 60. Here he has heat conduction in a thin circular ring. So let me talk to you about how that problem goes. It was supposed to be circular. Oh well. So,
heat conduction in an egg.
so this, as he sells this, he says it involves both sines and cosines, which is kind of neat. And so the top is going to be x equals to L. The bottom is going to be x equals to minus L. If you want, you can think of it as he's taking, you think of it this way, he's taking the, not the scale, x equals L up here, x equals minus L here, and he's just bending it into a circle, like that. And then, but, now,
So
we're gonna
aren't touching?
that's where we're getting to. And the reason we're using 2L rather than L is so that, as he explains later, it's so that he gets the same sort of formulas for the eigenfunctions. Alright, anyway, so let's see here. The radius of the circle is what?
Circumference is L.
Is
L
so
divided by 2 pi.
yeah.
That's radius.
You say L divided by 2 pi?
Yeah.
L over pi, yeah. So because we have 2L, so
Oh, yeah.
yeah. Anyway, so excuse me. That is the problem. Now, your question. Let me get to it here. He says, if the wire is thin enough, it's reasonable to assume the temperature in the wire is constant along cross sections of the bent wire. So we're assuming the wire is skinny enough that essentially the if you look at a little cross section here, we've got equal temperature on that. Okay. And so the flow of heat along the wire, for the usual reasons I never have really explained, but it has to do with conservation of energy. Partial U partial T is equal to K partial squared U. So this is just the heat equation I'm writing down, right? So that's how the local flow. So he says, we have assumed that the wire has constant thermal properties and no sources. And he says, let's assume that the wire is tightly connected to itself at the ends, and the conditions of perfect thermal contact hold there. So to answer your question, Jess, we are going to do like that, yeah. Apparently Audrey could do this for us. I was not aware of Audrey's second existence as a welder. I found out about that today. It's interesting.
Cool. Really?
Yeah. See, girls think that, like, if they put makeup on right, or if they wear the right pair of pants or something, men care. But when a man hears that a girl welds, it's like, that's interesting. I want to know more about this person. Right. Anyway, I digress. Let's see here.
I have a TED Talk you should watch. I need to send it to you now.
All right, so all right, once you connect it, we have a boundary condition then, right? So basically, U of L comma T should be equal to U of minus L comma T for all T, right? Because the temperature should match where it's joined, right? The temperature should be continuous there if it's in perfect thermal contact. And also, the thermal conductivity should be the same. So partial U, partial X at L should be equal to partial u, partial x, and minus L comma t for all t as well. So those are the boundary conditions that we face. All right. So then, the problem then is, if you're given, right, an initial temperature distribution on the spring, then how does the temperature evolve? Solving this heat equation will answer that question specifically, right? So here's basically the problem. Given all this setup, and say u of x comma 0 equals to f of x, some given initial temperature distribution, find the temperature at time t. Right? That's kind of like what we've done before with heat equations, right? So let me run through it since it's been a little while since we've done that. So to use Haberman's notation, he separates by phi times g. He lets u equal to phi of x times g of t. So what's that tell you? That tells you u sub t is equal to phi g prime, and u sub x equals to what? Phi prime prime g, right? So if we plug those in, we get, let's see what we get to. We get, sorry, brain not working, phi g prime equals k phi prime prime g, which of course gives us g prime over g equals to k phi prime prime over phi, right? Making that the separation of variables. Now, on the left-hand side, we have just a function of time. On the right-hand side, we have just a function of x. So it must be that this is equal to a constant, and we call that constant here. Let me see here. What's he do? Well, not sure what he does. Just a second here. I'm trying to line up my notation with his. Minus lambda k. Minus lambda k. I think he puts the k over here. We can do that. I mean, put it wherever you want. It's constant. And I think he calls this equal to minus lambda. I think is what he does.
I think you're right.
Yeah, that's his choice of labeling the constant.
Can you say it was easier for some future use with a negative, or?
Yeah, he's anticipating what appears as non-trivial solutions to the. He wants his lambda to make. He's trying to engineer it so the notation transcends a particular example and it goes across a bunch of examples. I'm less married to that idea. Anyway, so long story short, of course, we've got g prime equals to minus lambda kg. So that gives me solutions like g of t equals to e to the minus lambda kt, right? Solutions like that. And on the other hand, you've got phi prime prime plus lambda phi equal to 0, right? Which gives me different kinds of solutions depending on what my choice of lambda is, right? I've got 3 different things to think about in principle. I've got lambda equal to beta squared, I've got lambda equals to 0, I've got lambda equals to minus beta squared. So that gives me phi equals to like a cosine beta x plus b sine beta x. This gives me phi equals to a plus bx. This gives me phi equals to a cosh x plus b sinh x. These are the three worlds in which we can live depending on the choice of the characteristic value. The actual choice that's made for us, as we're looking for these so-called product solutions, these eigenfunctions as he calls them, which I hope to make more explicit for you guys in the weeks to come when we cover the Sturm-Liouville material. This is, well, and then we have boundary conditions though, right? Boundary conditions. So, let's see here. How does he say it? He says that this condition translates for the products as what? So like if you look at it, when you plug in time t, you get like e to the minus kt, and then plugging in L, you get like phi of L. So basically you get an exponential t both sides, doesn't do anything. So this just translates into the corresponding boundary condition. Phi of L is equal to phi of minus L. And this of course translates into the corresponding boundary condition phi prime of L equals to phi prime of minus L. So you got this pair of boundary conditions. Alright, so what? So then, alright, so what's he do? He's like, these are mixed type. He says these are referred to as periodic boundary conditions. Alright, so, yeah. Oh, these horrible square root lambdas all abound. Oh, awful. He doesn't say anything about it, but basically, I mean, he doesn't say much about it, but basically the Cauchy and Cinch solutions don't amount to anything. So we could investigate this, but this goes nowhere.
Why is that?
Well, if I put phi of L equal to phi of minus L, and if I put phi prime of L equal to phi if I impose these boundary conditions on this solution, you find only the trivial solution exists, okay?
No.
But on the other hand, if you put phi of L equal to here, right, you get a cosine beta L plus b sine beta L equals to what? Equals to phi of minus L, right?
Mm-hmm.
What is phi of minus L then? A cosine beta L, right? Minus b sine beta L by using the oddness of sine.
Mm-hmm.
So these guys cancel, but this implies that 2 times b sine beta L, right, equals to 0, which implies either that b is equal to 0, right, which would be fine because we still have a, or and it says that beta L is equal to n pi for some integer, all right? So either we're forced that beta is equal to n pi over L, right? So therefore, this forces us to either go, well, let me just say that, all right? On the flip side, phi prime of L is what? Differentiate, we get minus a sine, minus a beta sine beta L plus b beta cosine beta L is equal to, so the same thing, but you got to plug in minus L, right? So that gives you a beta sine beta L plus b beta cosine beta L, using the fact that sine is odd and cosine is even. So in this, the derivative boundary conditions, you see what happens, there's no information, you get no information about B, right? These just cancel, right? And what does it tell us, though? So B could be whatever, all right? And A, on the other hand, we get 2A beta sine beta L. It's forced to be 0, which either says that A is equal to 0, right? Or it says that beta L is equal to n pi. So you start putting these two things together, right? Because we're looking for non-trivial phi, which solve the boundary conditions, all right? So you just chase down some cases. Once you guys are with me, I'll walk through them. Are you ready? So if B is equal to 0, right? That forces us to look for A not equal to 0 solutions, right? So going over to here, this doesn't work. We're forced to go to that condition. So it forces beta L to be equal to n pi. Okay? Conversely, if I say that beta L is equal to n pi over here, right? Then I think, well, I mean, anyway, then, so, well, I guess the point was, logically, either beta is equal to 0 or it's not equal to 0. If beta is equal to 0, you're forced to have n pi. If beta is not equal to 0, you're forced here to have beta L equal to n pi. Anyway, whatever happens, you're forced to have beta times L equals to n pi. And you could either have sines or cosines appear non-trivially, depending on the choice of A and B. So in short, your so-called eigenfunctions, phi n of x, look like an cosine of what we got? Lambda with beta squared. Beta is equal to n pi over L. So you got cosine n pi x over L plus bn sine of n pi x over L. All right, we get all of that from, excuse me, the positive lambda case as he denotes lambda. Right. Now lambda equal to 0 gives you a solution. It's easy to see it just from looking at this. How can we get phi of L equal to phi of minus L in both the derivatives matching? Bx ain't gonna work. That's out. But constant, well, constants are equal to constants everywhere, and they differentiate to 0, so no harm to foul there. So basically, we just add a0 from the middle case. Well, this is the nth term, and then you have the 0th one would be equal to a, just a sub naught, right? And so these are sort of fundamental eigensolutions to the boundary value. And then, as usual, we add these together and use the term-by-term theorems in the next chapter, ultimately. But basically, the solution will have the form u of xt will be equal to like the sum, you know, and fine, I was about to throw in 0 into the sign, but I'll be a good citizen and write the a sub 0 out here out front. A sub 0, fine, plus the sum n equals 1 to make it interesting. 1 to infinity of appropriate coefficients. And so there you go, that's the general look of the solution. And then to fit the initial conditions, we do what we always do, which is what?
Fourier.
Right, then you find the full Fourier expansion of f of x, and that tells you what to choose for the coefficients a sub n and b sub n to fit this the given initial data. Now you can't just put anything you want there for f of x. What patterns? I mean, what property do you need for? Well, I guess. Excuse me. I mean, for this to be a reasonable initial temperature distribution, what do you need? You need f of 0 equals to f of 2 pi, among other things, right? And I think you also need that f prime of 0 is equal to f prime of 2 pi, if I believe. You know, otherwise the initial temperature would be inconsistent. I guess you could maybe get away, I don't know if you can you get away with not doing these and then these will be imposed long term? I don't know, that seems dangerous to me. Just a second. Alright, so that's basically it. And then of course, well I'm sorry, that's not it either. I'm an idiot. Times what? This has got no time dependence. So E minus, minus
Yeah.
what was lambda equal to? Lambda we decided was
Beta squared.
lambda's beta squared. Oh, it's quite awful, isn't it? Minus n squared pi squared k t over L squared? Yeah. Now, good news. Thankfully we don't need that over for this term, you know. But yeah. I don't think we do anyway. No, lambda equal to 0 in that case. So the yeah. That's just the constant solution there. But to, you know, I mean, it's well, I was being a little bit too flippant there. The Fourier analysis is still pretty involved here, right? Like, I mean, when you plug in u of x comma 0, what's that give you? It gives you a naught plus the sum, right? Of the put time equal to 0, right?
Mm-hmm.
Well, I guess it just gives you that, doesn't it?
Throws the exponential away.
Yeah, it just throws the exponential away. Yeah. Never mind. It is just all that. Yeah. Oh, it's the full Fourier series, right? So we need to do lots of integration to figure it out for a specific example. All right. So that's basically that.
Is like a sub naught, is that also, so it looks like this, like the function obviously, like it could, like kind of like, almost like converges, and we can pretty much tell it's going to converge to a naught given sufficient time, right?
Well, it does seem that way, doesn't it?
So does that mean like the function is like, is this system is completely independent from everything around it? Like it's completely insulated?
Yeah.
So I'm just wondering.
Hmm.
I'm just trying to like think out
That's
loud.
true. The heat flows in the rod. I think that's there's conservation of. Well, could that be right? Huh.
But it tells us that everywhere in the rod, no matter where you're at, every point is going to converge to a naught. So, given
Yeah,
a
that
very long
does-
amount of time, the entire rod's going to be at a naught,
Huh.
right? I mean,
I guess could the whole.
Sensing it. Entropy and stuff.
yeah.
Huh. Hmm. Yeah, I want to agree with you. Let's see here. Do you guys have your? Let's see, I want to talk about Laplace's equation on a circular disk now. I'm worried that I'm going to get into trouble because I think you might need to use the... Now I'm trying to remember from my reading earlier. You might... Well, I think it's okay. I think it's still periodic boundary conditions. I was worried it was non-homogeneous boundary conditions. But I think we're okay. Let's talk about Laplace's equation for a circular disk, yeah. It'll take me longer to discuss the non-homogeneous boundary conditions. It's like just a lot of writing and it wouldn't be that interesting. I actually have a problem or two worked out for Laplace's equation on a disk already in my previous notes. It's like I have an explicit example, or maybe just example worked out. It's really fun. So let's work on that. I mean, we can go further on this, but we already have the techniques we need to solve this for a specific thing. I think it's kind of nice to look at this in terms of theta t instead of xt here, I will admit, but anyway. I do think Hederman is not wrong to use x here because it makes it tie into our previous work in the heat equation more tightly. Ooh, I probably should have. Oh well. I will regret something I just did, I think. Alright, so Laplace's equation. In two dimensions. In fact, that's all we've done, really. Okay, so we could write del squared u, right, which is the divergence of the gradient of u, if you like. So, of course, in Cartesians, it's uxx plus uyy. But what's that look like in polar coordinates? In polar coordinates, that's 1 over r, partial r, partial u, partial r. You'll forgive me if I don't derive this today. That's what calculus 3 is for. Plus 1 over r squared, partial squared u, partial theta squared. So that's what the Laplacian looks like in polar coordinates. So setting that equals to 0, that's what Laplace's equation looks like in polar coordinates. Now, the question here is, he's like, suppose we have a thin circular disk of radius a with constant thermal properties and no sources, temperature prescribed on the boundary as illustrated. If the temperature on the boundary is independent of time, then it's reasonable to determine the equilibrium temperature distribution. The temperature satisfies Laplace's equation. Thank you. And the geometry of the problem suggests that we use polar coordinates. All right. So let me see if I can't draw a picture. So, all right. So basically, here's r equals to a. So u of a comma theta equals to f of theta is given time independent temperature on the boundary. All right. And so then what? We want to solve Laplace's equation given that boundary condition, right? That's the idea. And this is related to the problem I've worked so far today because of why. Like what, you pick, I mean, you can kind of, how does he say it? guess he thinks of it as somehow related to the rectangle. He sort of thinks of this. I don't know if I like that though. I mean, you can think about cutting it, you know, here. And then you go from where to where, from like, from minus pi to pi, you know, and it made sense when I read it earlier, tried reading it.
So he's treating those little sections right there as like disks. They're all going to maintain the thing, kind of like we assumed it in the ring earlier.
No, just the outer thing. Just the outer ring. It's a given. Is it the R equals to A? There's a given temperature distribution. Now we're going to find, given that fixed temperature distribution, what does the temperature have to look like inside?
Oh, okay.
Inside the disk, in order to satisfy that boundary condition.
Okay.
And Laplace's equation. Well, here's what he says. He says, the introduction of polar coordinates requires some discussion that will illuminate the use of the method of separation of variables. If we solve Laplace's equation in a rectangle, then the condition necessary is at the endpoint of the definition of the variables, x equals 0, L, y equals 0, h, coincide with physical boundaries, but for polar coordinates, you know, we're going, if you want to think about polar coordinates that describe this, we've got some, I mean, in polar coordinates, what is the disk? What he's saying is you've got 0 less than or equal to r, you know, less than or equal to a, right? But then there's an ambiguity here, right? Like minus pi less than or equal to theta less than or equal to pi, so to speak, or, but that's a choice, right? That cutting it at pi and linking it to minus pi is just one of many, many possible ranges of theta we could have picked there, right? So what he says only r equals to a corresponds to a physical boundary, right? He says we need conditions motivated by the considerations of the physical problem at r equals 0 and at theta equals to plus or minus pi. All right. So what's he say? Anyway, he's just trying to motivate something that other books will. Some books will just write these down like these are necessary, just considering the physical aspects of the problem. So, physically speaking, we just changed coordinates, right? There's really no reason. There's a singularity in polar coordinates at the origin, right? That's a coordinate artifact. So one of the things we should want is we need that the u be less than infinity near r equals to 0. So in other words, the solution should be bounded at the origin, of course, right? And 2, if we're going to work with minus pi to pi, we do also expect that, what do we expect? We expect u of, let's see here, we expect u of r, u of,
R pi equals u of r negative pi?
yeah, right. And also, because those are it's a mathematical, that's just where we're redefining the angle, right? Nothing should happen there, physically speaking. We could just as well have put the cut somewhere else, and there shouldn't be any discernible discontinuity in the temperature or the flow of heat across that boundary. Of course, you recognize these. Hey, these are the mixed periodic boundary conditions we were just studying for the circular ring, right? I mean, just instead of L, we've got pi, but that's it, right? So, but this is not the same. I mean, it would be almost, but we were studying a different differential equation there, right? We were studying the heat equation. It was a little bit different, right? We were studying, just a second ago, we were studying, what was it? UT equal to K UXX, is that right?
Yeah.
Versus, So yeah, similar boundary conditions, but vastly different problem. This is a two-dimensional problem also, right? We're trying to find not just u as a function. We're trying to find u as a function of r and theta. But this is also quantitatively different because it has time dependence, right? This is a time-independent problem. So as much as they're similar, I mean, they're similar in the periodic boundary conditions, but that's about it. Okay, so then what?
And just start. Can we start separating again? Or no?
Yeah, I think so. So now he did something sneaky here. What's he do? All right, I tell you what, I'm gonna do. He does. I'm just gonna. Let me just bite the bullet, and because I think he's doing something crafty to make it slicker in the book. I'm gonna be less slick, and let's just multiply this thing out. Let me differentiate this thing out. What is it?
I mean,
I'm not trying to.
Once we separate, right?
You can look at the book later and see how he does it from this perspective, but I think I'm going to do it from another perspective instead.
Yeah.
This is 1 over r, and then differentiating that gives me what? Product rule, right? So it gives me 1 over r, partial u, partial r. See, because this differentiates to 1, and then plus 1, because r over r is 1, second derivative of u with respect to r squared, right? Plus 1 over r squared, partial squared u, partial theta squared. All right? That's equal to 0. This will be easier for me to do separation of variables on, all right? You guys will remember the periodic boundary conditions. I'm going to erase them. It's doubtful we'll get far enough to really put those into practice here anyway, so it's okay. So yeah, we're going to let u equal to, let's say, I'll put it up here. We'll put u equal to, what do we want to do? Say phi of r and let's say t of theta. Sound good? Let's do capital R of r. Why not? R. All right. So, I'm sorry for that. But not that. Sorry. So then 1 over r partial u partial r is r prime t. Plus this guy gives me r prime prime t, and then plus 1 over r squared, r t prime prime, because that's my theta derivative, equal to 0. Let's see here. So multiply this by r squared. We get r squared r prime prime plus r prime equals to what? Equals to minus t prime prime. And to be clear, I did what? I divided by So again, what I'm doing here is I'm moving, multiply the whole thing by r squared, move the t prime prime term over here, gives me a minus. Then I divide the whole thing by rt. The t's cancel on the r derivative terms, and the r cancels in the t derivative term. And then now we're to our happy place. This is just a function of the radius. This is just a function of theta. So the only thing which is commonly both a function of r and both a function of theta non-trivially is a constant. So this must be equal to, let's say, lambda. And so we find ourselves faced with r squared r prime prime plus r prime I'll put a minus here, it just feels right, plus lambda r equals to 0, and I guess t prime prime. Oh, you know what? I don't know. I don't know if that should be plus or minus. I just don't know. I'll just leave. What did he do? What did he do? What did you do? Show yourself to me. Where'd you go? Did that change page? Yowzers. Oh. Come on. He comes to the conclusion that lambda, let's see, d squared phi minus, okay, no minus. So that puts a minus here. Alright. So t prime prime plus lambda t equal to 0. Okay, so that, okay, remember our boundary condition, what was it? It was, do you remember, it was, one of them was that u of, why did I erase that? I'm an idiot.
U of r pi equals
U
U
of
of
pi.
r negative pi.
Was u of r minus pi, right?
Yep.
That holds for all r, so basically that forces t of pi equal to t of minus pi. And also the other one gives you t prime of pi equals to t prime of minus pi. So working that all out basically forces lambda to be equal to n squared. And so then that lends you to solving r squared, r prime prime, plus r prime minus n squared r equals to 0. And the theta, the t, so like t of theta is something like a constant a cosine n theta plus b sine n theta. That's the the eigenfunctions in theta are just sums of sines and cosines, and this is what you have to solve in the radial. What is that? Do you guys know?
We factor the roots.
This is a Cauchy-Euler problem, or the so-called equidimensional problem. The solutions have the form r equals to, like, well, I usually use r for this, so it's kind of funny. I usually use like y equals x to the r for my Cauchy-Euler, like my typical Cauchy-Euler solution, which is bad here because I'm using
Big R's.
so I want to use r equals r to the, let's say, c, just to be boring, and that's bad. So that will give me like this gives me c times c minus 1 plus c minus n squared, all times x to the, listen to me, x, listen, r to the c equal to 0. This Cauchy-Euler problem, it gives you two solutions. And then that's where the bound, this is it's really kind of cool because like one of the solutions might blow up at the origin, you throw that one out. You want the one that's finite at the origin. So like if you've got some of them will have like log r in them, those ones are possibly no good, depending on, unless you got like L'Hopital's rule to put it to bed. Let's see here. Yeah, so I mean for a specific so you gotta work through that to find.
Is it just c equals plus or minus n?
Is that what that is?
I think so.
Oh, cool.
I do believe.
Oh yeah. Cool, so basically r is then equal to either r to the n or r to the minus n, right? But of course one of those blows up the origin and one of them does not. So we choose this one, I think. Right? Because that one 1 over r is divergent at the origin, so we get rid of that one. And so you put it together, your solutions look something like the nth one of r theta would be something like r to the n times a. There's no a in here, sorry. Goodness gracious, yes there is. Here. Just give me a second here. U equals to something I haven't figured out yet, plus the sum n equals 1 to infinity of stuff like r to the power n, an cosine n theta, plus bn sine of n theta, like so. Now how about n equals 0? N equals 0 gives you c equals 0 2 times, right? So that gives you r equals to a constant, or log r. But again, log r we throw out because, I'm sorry, what I said about L'Hopital's rule a bit earlier was nonsense. So I think we just get a constant times, well, just a constant, right? So I think that, generically speaking, is what the solution would look like to Laplace's equation on a disk in terms of polar coordinates. Now, let me just skip a second here. Does he? Oh, what he does is he just throws n equals 0 into the cosine terms, and he starts the sine one at 1. Now, to actually put this into practice for a specific problem, we would actually have to find the full Fourier expansion of f of theta by the usual integrals. Let me show you guys something, and then we'll stop if I can find it. Just give me a second here to find it. Did you guys have a good weekend? I'm still horribly behind in abstract. I have so many notes. I got notes to write, and then
Would it instead be r?
I gotta scan something before I leave. What's that?
Would it instead be r to the negative n because
I can scan when I get home.
doesn't that formula blow up? Wouldn't it be the other one?
R to the
Because
what?
the sum part, once you get like the Fourier stuff, wouldn't that part of the equation just blow up, which is not what you want?
Why would it
Do you
blow
want
up?
it to converge? Well, because as n approaches infinity, that term over there is going to
But
get
as
huge.
n approaches infinity, these coefficients are getting smaller, so
It balances out.
or it balances out in some systematic. That is the magic of the method. The balancing of the infinite with the finite. Alright, give me a second here. I will find it. I'm going to find it. Alright, so we are looking for. Yeah, this is the end of the road in my solutions to. So if you look at my old homework solutions, here I solve. This is it in there? Is it in this? I can't tell if I'm in the screen or not.
Sorry.
Oh, let me cheat a bit.
Pretty good job so far today.
So can you guys see it? Well, this is really challenging because it's like it's all backwards of what no, that way. I'm not very fast with this. Anyway, so this is, I can't quite make it. I need a bigger screen on my camera. This is the Dirichlet boundary value problem on a disk, right? What are my f of theta is what I have there, absolute value of theta. So like it's temperature pi, and then it goes to 0 back over. So like, you got like maximum temperature here, and then it symmetrically drops to 0 as you go like this way. 0, 0, like that, right? So that's my anyway, so I go through the stuff we just did basically, and so I derive what we just derived. And this is tricky. I'll eventually get it. As you can see, the star-star equation there is exactly what we just found. And then what do? I find the Fourier expansion of f of theta equals absolute value of theta. Here are the inglorious details. So you can see 0, looks like the 0th term is it pi?
Yeah.
You guys can see better than I can actually.
Yeah.
And the
An is equal to negative 4 over pi n squared.
a sub n minus 4 over pi squared, and then how about the b sub n's?
You're not there yet.
Are those, maybe those are 0. Ah, yay, odd function. My favorite kind of calculation. 0. Or if you're my friend Topoma Sarkar, you might say 0. Let's see here. Hope he's watching this. Very unlikely. Let's see here. So there you go. Put it back together. Those tell me the coefficients I needed to put the initial condition together, and then I know that a sum of that nature by the term-by-term differentiation stuff, which I've sketched some of the proofs of for you guys, but I really haven't completely explained. Basically, you can plug that in and take derivatives of it term by term, and you can see that it solves Laplace's equation on the disk and fits the boundary conditions, and there it is. And so this is kind of, so there's the actual solution right there to the Dirichlet's problem on the disk like that.
I can see this.
What's that?
Can I get a better look at that?
Oh yeah, go for it.
I'm just... I'm trying to decide if it, see if that converges or not.
Oh,
I'm
well
just
you got
concerned about that.
you got cosine of stuff there, right? But
Yeah.
as k goes to infinity, you got 2 to the 2k minus 3 there,
Yeah.
and a
that
2k
gets
minus 1 squared. That coefficient gets super tiny
Okay.
as you go on. And r does not go to infinity. R is bounded between 0 and, whatever the radius of what the disk was we were looking at,
Yeah.
wasn't much. And those cosines, well, they just go between plus or minus 1, right? So, sort of, intuitively, it's kind of like sort of a jilted alternating series. So, I mean, I don't know, its convergence, I think, is pretty mellow. But, yeah. This technique, though, that we just ran through here, for circular domains, you can change the polar coordinates. And when you change the polar coordinates, the Laplace equation ends up giving you a Cauchy-Euler equation in the radial separated solution, and then just like periodic solutions, sinusoidal solutions in the angle. You put those together, and that allows you to solve problems on like a disk. And I think similar things would apply to, say, if you're solving the wave equation on a disk. You could change the spatial part to polar coordinates, then you'd have a time solution. But the wave equation, like the two-dimensional wave equation you could solve there, would be amenable to these techniques. So hopefully sometime soon I'll figure out how to derive the wave equation, and then I'll show you. I was reading in the book, and he talks about the derivation of the two-dimensional wave equation, like waves on a membrane, all right? And I just found it fascinating. He's like, and now we use Stokes theorem. And then he comments, this is the only place in this whole book we use Stokes theorem. I was like, what? That's the whole, like a 500, 600 page book on PDEs. We only use Stokes theorem in one place. I feel like,
Maybe he has something against Stokes.
because I personally, I could see arguing that I'm using Stokes theorem where I explain the connection between Maxwell's equations and the wave equation. Like, that's another place I feel like maybe, but on the other hand, if you just take not an integral, but a differential approach to Maxwell's equations, then you wouldn't use a Stokes theorem argument there like some of the elementary books do. So, I don't know. Anyway, thanks guys.